this section we will be looking at the length of a curve, or as the notes call it here, arc length. So this is quite possibly the easiest section in all of calculus. It is all calculator work, it is very easy setup, and there are a few exceptions to that, but we're not going to take a look at too many of those today. So very basically, arc length is how long a curve is, and it's impossible to measure a curve with a straight edge, like a ruler. Here we have a picture, and there are all these different straight line segments between these different points, and those give an approximate length for this curve. Now obviously it would be an estimate, and in this case an underestimate, since all of these red lines are shorter than the blue lines that they go between. So these secant lines are all shorter in length that navigate this curve here to give us an approximation. Okay, so just like everything else in calculus, how do we get a more exact answer? We use more points. We make our points closer together, really. We get that length between A and P1, P1 and P2. We get those closer and closer and closer to 0. Doing that, we will get an absolute exact answer for the length of this curve. And how do we do that? Well, we use calculus to do that. So they come down here with this formula, and that's the distance formula down there, the square root of delta x squared plus delta y squared. We've known that since geometry. So we have that old formula in there, and we're going to build off of that. Not going to go through the derivation, but that's where the formula that we're going to use today comes from. And here is the formula that we are going to use. So if f is continuous on AB, then the length, called arc length, of the curve of y equals f of x from the point A to the point B is the value of the integral a to b square root 1 plus f prime of x squared dx. Or you can write it the other way, dy dx squared dx. So we have this integral, and again, it's essentially coming from the distance formula. That's why we have the square root and the quantity squared, and we are going to need a calculator to do this integral. This would be a very challenging integral to do by hand with the square root. Would require u substitution, possibly an integration by parts at some point. We're not going to mess with all that. This is calculator work. Stick to the calculator, let the calculator do the bulk of the work for you. It does not matter what letter you use to do this. If your equations are functions of x, great, use this version. If your functions are x in terms of y, so let's say x equals f of y, then you can do the exact same formula. The length in terms of y is the square root from a to b. We'll call it c to d to give different letters there so we don't overlap. So the integral from c to d of the square root of 1 plus, we should probably call that g, but I'm not going to go back and change to this point, f prime of y, quantity squared, with respect to y, which is the same thing as c to d of square root of 1 plus dx dy squared with respect to y. So it does not matter what letter your equation is in. We use this same formula, and it's just the derivative quantity squared, and then you put this all in. Okay, so let's take a look at a few examples here. We have this curve. It is 4 square root of 2 over 3, x cubed minus, or x cubed, x to the 3 halves. There we go, quantity minus 1. So the length of the curve is slightly larger than the length of the line segments joining A and B. Great. That's not really a lot of information there, and it is, they don't give us kind of an example or anything like that, so I think I've got one that I'm going to pop in here. Maybe not. Let me go grab that. Oh, and there's the formula in terms of y. So I'm just going to go grab that other example that I was looking at, and we will use that to go through and actually find the length of a curve here. Okay, so we'll do that one in a second here. I just want to get us started off with an example that lays everything out for us here. So we have this, and now it's got the answer, but that's okay. The length of the curve, y equals x squared from 0 to 1, we use the formula that we just looked at, and we plug everything in. They're talking about using int. These are old notes. We are going to use the calculator using the numerical integral solver. We're going to still do all of that. So what we're going to do, again, is use this formula, and the function is x squared. the derivative of that function is 2x. So there's two ways that we can do this. There's the easy way, and then there's the even easier way. I prefer the even easier way. It's more buttons on the calculator, but in my opinion, it's even easier. So we'll look at both ways. So we have the formula, again, is the length, capital L, is the square root from a to b of the integral from a to b, square root of 1 plus dx dy quantity squared dx. So the length from 0 to 1, those will become our limits. So the integral from 0 to 1 of the square root of 1 plus the derivative of our function, and they've got that laid out for us right here. The derivative is an easy one, 2x. So we'll put 2x squared dx. Again, at this point, we don't want to try to evaluate this by hand. It's going to be very, very challenging to try to do this by hand. Got the calculator up for a reason. Plug this into the calculator. That's where we're going to get our answer. Okay, so we set it up 0 to 1. And we've got the square root of 1 plus this, how to get all the way out there? I don't know. We'll try this again. So 0 to 1 of the square root of 1 plus quantity. Make sure that's a quantity. We don't want it 2x squared. We want 2x quantity squared dx. And it should give us the answer of 1.479. Okay, let's get a decimal answer. There we go, 1.4789. And that is super easy. The derivative was easy enough to calculate by hand, 2x, pretty straightforward there. So here's an even easier way to do this. What we can do, instead of doing the derivative, we can let the calculator do the derivative for us. You might be saying, well, that's kind of foolish in this one. The derivative is easy enough. Why don't I just take it by hand? Great, but what if we have a more challenging curve like the example that we looked away from? That is going to be a lot more challenging to do by hand, and if you've got the calculator, let it do the work. So we're going to use ddx of x squared dx. Like I said, it's a few more buttons to press in the calculator, but it's going to save us some time, so we'll see what that looks like here. So we have the square root still of 1 plus, and now what we're going to do is go into the menu, pull out the derivative, ddx of x squared. I do think I need an extra parentheses, but it should automatically make it for me. No, it didn't. So we'll put one here. That's the only thing. That has to be in parentheses, the ddx, so it gets squared on the outside. And then dx. I'm going to go with the approximate answer, so Control Enter. And we get the same thing, 1.479 with the rounding. Okay, so that is the way that I prefer to do them. It saves you the time of going through the derivative. If it's a complicated derivative, it saves you a load of time. It's just a few more buttons to press in the calculator, making sure we've got these parentheses here before the ddx and close before we square. Okay, so unfortunately on this set of slides, that's the only problem I have with the work and example, but we can take a look at these and set them up and see what we get. So we'll do this one kind of together here. If you want to pause it and take a go at it, go for it, but I'm just going to work right through it. So the function is right here. So our length is the integral. We are on the x values, so from 0 to 1, of the square root of 1 plus the derivative. So again, I'm just going to write ddx. I'm not going to try to take that derivative by hand. Could I? Sure. Do I want to? No. So ddx of 4 root 2 over 3, x to the 3 halves minus 1, quantity squared dx. I wrote a little bit into that, but that's okay. So let's see what we get here. So we have the, man, I do not like this calculator today. Menu for 3, 0 to 1 of the square root of 1 plus, I don't know why it keeps jumping, 1 plus, now we're going to get the derivative, ddx, and I forgot to put my parentheses before it again, so don't forget to do that. ddx, and now we're going to plug all of this in. So I am going to use the fraction button here just to get a little help. 4 square root 2, and that's over 3, x to the 3 halves, minus 1, quantity squared, those are some tall parentheses, and dx. Okay, so 2.16, we'll call it. And if we look at this, hopefully we're in the right ballpark. If we take a look at the height there, it is 0.89. So the distance formula, again, would be the square root of the difference of the x's, so that's 1 squared the difference of the y's, which is 1.89 squared. So let's see what we get when we do that, because they did ask us, or they did tell us at least, to be slightly larger than the length of the segments. So we have 1 squared, which is 1, plus 1.8 quantity squared, 8.9 quantity squared, and we get 2.13. That's fantastic. We are within 3/100ths of the secant line there. So that is a good answer that we got for the length of the curve. So our approximate length of the curve is 2.16. We'll call that repeating. Okay, so there are a few more examples here that we'll look at. If you want to go ahead and pause the video before them and try them out, be my guest, and we are going to work them the way that I've been showing with the derivative in the calculator. Okay, so for this one we have the integral. For the length we have the integral. The x value there is 1, and the finishing x value is 4. The square root of 1 plus, and then I'm going to go ddx. We could do this derivative, it's not too challenging. I'll do it both ways just to verify. ddx of x cubed over 12 plus 1 over x, quantity squared dx, which should be the same thing. The derivative of this is x squared over 4. The 3 comes down, reduces with the 12, minus 1 over x squared. So that should be the same if we plug that in here. 4 minus 1 over x squared. But again, it's not necessary to take that derivative, especially since you're using the calculator. Taking that derivative by hand just brings in another chance to get something wrong. And no one wants to get something wrong. That's a simplistic sort of part of the problem. We have x to the 4th, x squared over 4, there we go. We have minus 1 over x squared, and we'll square all that, and we'll go dx, and we get 6 point, I don't know what, maybe 6.0, it just stopped. So that is our approximate answer. Let me see if I get anything different. What in the world? If I just, nope, 6, okay, so it is 6. The exact answer is 6 apparently. So we're going to do this again, many 4, 3, from 1 to 4 of the square root of 1 plus the parentheses first, I got it this time, derivative with respect to x of x cubed over 12 plus 1 over x. Out, quantity squared dx. And we get 6. Okay, great. So we have the same answer both ways, again verifying that the calculator will do the work for you. Don't waste the time if you don't need to. So here we go. They do actually give us the formula with respect to y here at the bottom. They did change everything from a to b, c to d, and then from f to g. So it's the exact same equation. They've just rearranged the letters to show you that they're using a different variable y now for this. So why would we use a different variable to do this? Well, the set of notes we have here doesn't offer any explanation for it. So I'm going to jump over to a different set of notes here that kind of does. We're not going to look at these in this set of notes, but there is another video on this channel talking about these two examples here. So if there's a vertical tangent, so we have this curve here, x to the 1/3 power. There's a vertical tangent in the middle if we would draw this curve. And what would happen there is it would sort of break this process, and we wouldn't be able to get a length of the curve there. Since we're taking a derivative and it's undefined at 0, it would give us a lot of problems. So what we would need to do is either break the length of this into two separate pieces. So take the length from -1 to 0, and then add that to 0 to 1 length. It's symmetric, so they should be the same, so you can just double it. But for any function that has vertical tangent, you could break it into two pieces like that. Or you could rearrange this equation to be a function of y. So cube with both sides and have x equals y cubed. Y cubed does not have a vertical tangent. We can take the derivative of y cubed. It's continuous derivative, so we would be in good shape there. So that is the reason really they give us the y equals equation to show us that we can switch the letters if there's a problem doing with respect to x, and then we should be good to go. So just to kind of show that off, we'll see what happens here if we go from -1 to 1 of the square root of 1 plus the derivative of x to the 1/3 quantity squared dx. And it gives us that orange or yellow box there. It says questionable accuracy. So it might be wrong. And that's a good thing that they give us. We actually, the calculator is able to handle it, which is awesome. Doing it with questionable accuracy 99 times out of 100, maybe even more, this calculator is going to be correct when it gives you that warning with the questionable accuracy. On the off chance that it's wrong, you don't want to mess it up, you can do it the other way. Doing the y cubed will give you the correct same answer, most likely without the warning. So we'll just show that really, really quickly here. I knew I said I wasn't going to spend a lot of time on this, so let's do that really, really quickly here. The square root of 1 plus the derivative with respect to y of y cubed quantity squared dy. So now it gives us that answer without the exclamation point. And you see they are off by a, what is that, 10,000th there, 100,000th. So the answer is very accurate enough that we would round it 3 decimal places and still be okay. So it really is not a huge deal on that one with the vertical tangent. The calculator is able to handle it, especially the newer versions with newer software. They have learned to program around this. The other example here is getting around a corner. So this would be an absolute value, and the derivatives don't exist at that corner. So what we'd have to do with this function, and this is actually really easy because they are linear pieces, we'd have to break this down into a piecewise function, and that's something that we did very, very early in the year with looking at the corners as points of discontinuities on derivative equations. So that, if you want to pause, take a look at that there. I'm not going to go through that example. So back to the notes that we were looking at. So we have this here, and they say that we can use either version of this equation and get the same answer. So the graph of y equals x over 2 quantity to the 2/3 from 0 to 2 is also the graph of x equals 2y to the 3/2 from 0 to 1. So if we switch the letters, we switch the limits of integration from x's to y's. That's the only thing, is if you're going to change the letter, make sure that you use the correct integration limits from the correct axis. So that's the last thing we'll do on these. This went a little bit longer than I was hoping for. I thought this would be a very, very quick notes, but again, trying to make it a little more mathy. So we will take a look at this both ways. So the length with respect to x, and if you want to pause and set them both up, be my guest. The length is the integral. If we're going to do the x's, it's from 0 to 2. The square root of 1 plus, again, I'm just using ddx. I'm not going to go through and take the derivative. ddx of x over 2 to the 2/3, whole thing quantity squared dx. If we do it with respect to y, we're now using the y-axis numbers, so 0 to 1. The integral of the square root of 1 plus d dy this time of 2y 3/2 parentheses quantity squared dy. And we should end up with the exact same answer. If we don't, we got some problems. So we'll do the x version first. So 0 to 2 of the square root of 1 plus parenthesis ddx of x over 2. So we'll do another parenthesis in there. x over 2. Go out to the 3 halves, all the way out squared. We should be good there. That should be it. 61/27. Perfect. Just what I thought it would be. So we'll do this again with respect to y. So this is from 0 to 1 of the square root of 1 plus, parenthesis, derivative with respect to y of 2y to the 3 halves. Oh, I did that first one wrong. So I'm going to go back up and change that to this. These answers are not going to agree because I just realized that I switched the fraction there for the x over 2. So I've got that first one wrong. So this answer should be markedly different. Yes, and it is. So it is approximately 2.268. So let's go back up and change this one and fix it. That answer felt a little too exact. All right, so that should be 3, and this should be 2. And we'll see if we get 2 point something. There we go. So we get 2.26835. This one does give us a little bit of a fit here. The warning that it's questionable accuracy. This one, though, is accurate to those first 5 decimal places. So sometimes it throws that if there is a possibility that there was a vertical tangent or undefined location that it went around with the derivative, it's going to throw that just so you're aware. But again, 99 times out of 100, it's the correct answer. It's the answer that we're looking for. So we are good both ways there. Okay, so this last little piece they have here, diagrams for remembering the equation. Just look at the equation. It's really right there. It's really easy. It's just the square root of 1 plus the derivative squared. Super easy formula to memorize. In terms of all the formulas we've had, this is one of the easiest. It's on the calculator. I mean, you can even just store it somewhere in the calculator. So I wouldn't really spend time memorizing this part from the derivative or the distance formula, but again, that's where it came from. So they're showing us that at the end. So this is, again, super quick section to do it all in your calculator. If you really want to take the derivatives by hand, go for it, but I would suggest getting comfortable using the derivative function inside the calculator, making sure that you got all the right parentheses, making sure that you enter the equations correctly, but then you should be good to go with very little work to do by hand. So that's it for this lesson. Until next time.